Hello everyone, thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Thin Plate Buckling, and it is going to provide you a broad overview of plate buckling and also the analysis of local buckling of thin plate elements in compression. I am going to give you an overview of what I am covering today's video. First at all, we will have a look at some fundamentals of the local buckling of thin plate elements. Then move on to calculate the plate buckling. Then wrap up with conclusions. The behavior of compression members was assumed that no local distortion of the cross-section took place, so that failure was only due to overall buckling and yielding. This treatment is appropriate for solid section members, and for members whose cross-sections are composed of comparatively thick plate elements, including many hot-rolled steel sections. However, in some cases, the member cross-section is composed of more slender plate elements, as for example, in some built-up members, and in most light-gauge cold-formed members. These slender plate elements may buckle locally, as shown in this figure, and the member may fail prematurely, as indicated by the reduction from the full line to the dashed line in this figure. In this video, the behavior of thin rectangular plates subject to in-plane compression will be discussed. Next, we will introduce the simply supported plates. The thin flat plate element of length L, width B, and thickness T is simply supported along all four edges. Applied compressive loads N are uniformly distributed over both edges B of the plate. The elastic buckling load NCR can be determined by finding a deflected position, such as that shown in the plate figure, which is one of equilibrium. The differential equation for this equilibrium position is this expression. A solution of this equation which satisfies the boundary conditions along the simply supported edges is this expression of V, where delta is the undetermined magnitude of the deflected shape. When this is substituted into the differential equilibrium equation, an expression for the elastic buckling load NCR is obtained as this equation, which has its lowest values when n equal to 1 and the buckled shape has one half wave across the width of the plate B. Thus, the elastic buckling stress sigma CR can be expressed as this equation, in which the buckling coefficient K sigma is given by this equation. The variation of the buckling coefficient K sigma with the aspect ratio L over B of the plate and the number of half waves M along the plate is shown in this figure. It can be seen that the minimum value of K sigma is 4, and that this occurs whenever the buckles are square, M times B over L equal to 1. In most structural steel members, the aspect ratio L over B of the plate elements is large, so that the value of the buckling coefficient K sigma is always close to the minimum value of 4. Therefore, the elastic buckling stress can be closely approximated by this equation. Next, we will introduce the ultimate strength. A thin elastic plate doesn't fail soon after it buckles, but can support loads significantly greater than its elastic buckling load without deflecting excessively. This post-buckling behavior of a thin plate is due to a number of causes, but the main reason is that the deflected shape of the buckled plate cannot be developed from the pre-buckled configuration without some redistribution of the in-plane stresses within the plate. This redistribution, which is ignored in the small deflection theory of elastic buckling, usually favors the less stiff portions of the plate and causes an increase in the efficiency of the plate. One of the most common causes of this redistribution is associated with the in-plane boundary conditions at the loaded edges of the plate. The redistribution of the in-plane stresses after buckling continues with increasing load until the yield stress Fy is reached at the supported edges. Then yielding spreads rapidly, and the plate fails soon after. The occurrence of the first yield in an initially flat plate depends on its slenderness, and the thick plate yields before its elastic buckling stress sigma Cr is reached. As the slenderness increases and the elastic buckling stress decreases below the yield stress, the ratio of the ultimate stress FELT to the elastic buckling stress increases. Although the analytical determination of the ultimate strength of a thin flat plate is difficult, it has been found that the use of an effective width concept can lead to satisfactory approximations. According to this concept, the actual ultimate stress distribution in a singly supported plate is replaced by a simplified distribution for which the central portion of the plate is ignored, and the remaining effective width BEFF carries the yield stress Fy. It was proposed that this effective width should be approximated by this equation. Alternatively, this proposal can be regarded as determining an effective average ultimate stress FELT, which acts on the full width B of the plate. This average ultimate stress, which is given by this equation. Experiments on real plates with initial curvatures and residual stresses have confirmed the qualitative validity of this effective width approach, but suggest that the quantitative values of the effective width for hot rolled and welded plates should be obtained from this equation, where alpha reflects the influence of the initial curvatures and residual stresses. For example, test results for the ultimate stresses of hot rolled simply supported plates with residual stresses and initial curvatures are shown in this figure, and suggest a value of alpha equal to 0.65. From conclusions, what we learned: a slender plate element doesn't fail by elastic buckling, but exhibits significant post-buckling behavior. Because of this, the plate's resistance to local failure depends not only on its slenderness, but also on its yield strength and residual stresses. The resistance of a plate element of intermediate slenderness is also influenced significantly by its geometrical imperfections, while the resistance of a stocky plate element depends primarily on its yield stress. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,